So let's talk for a moment about these limits that we're going to use to solve the tangent line problem and to solve the area problem. And so to facilitate this discussion, I'm going to use a graph here. I want to keep in mind though that we could be dealing with functions where we have a picture of the graph. We could be dealing with data that's given to giving us information about a function in a table. We could be just given an equation for a function. So there's a lot of different ways we could be given the function. A graph is kind of the easiest way to kind of discuss the ideas, but these ideas would apply to any representation of a function. So when we're dealing with these limits here, the idea is we want to know what's happening to the function as the x value, or at least this in this case the x value, because we're going to be going along the x-axis here, as the x value approaches some particular number. So for example, I'm just going to pick the number 2 here. As x approaches 2, and it's important that we think of this as x approaching 2 and not x actually equal to 2. It doesn't matter what's actually happening at x equals 2. What matters is what's happening around x equals 2, so in the neighborhood around it. So as x is approaching 2, we're going to be looking at the function in this neighborhood, and from the left side, the function is approaching a y value of 3, and from the right side, it's also approaching a y value of 3. So as x is approaching 2, then the function itself is approaching 3. So we're looking at the values of the function that we get, so that's going to be the y values. So the notation is going to look like this. So we read this, the limit as x approaches a, so we say the limit as x approaches a of f of x equals L. So a is going to be some number. In the example I just did, a was 2, and then L is the value that the function approaches, so that's going to be 3. So another way of thinking about this is as x approaches 2, f of x approaches 3. All right, so this is the notation that we're going to use. So I'm going to go back to this graph here and look at a few limits here. So the first one, we want to know what's happening with f of x as x is approaching 2. That's the one we just talked about. So as x approaches 2 from the left and as x approaches 2 from the right, in both cases, the function's getting closer and closer to 3. It actually doesn't matter here that the value of the function is 3. It happens to be in this case, but it doesn't have to be. And then in this next example, that's actually really important because as we approach 4 from the left, the function's getting closer and closer to 1. As we approach from the right, the value of the function's getting closer and closer to 1. And so the limit is actually 1. It doesn't matter here that the value of the function itself, f of 4, is actually equal to 5. So this point right here doesn't matter at all when we're talking about limits. So limits are just what's happening in the neighborhood around the point, around that x value. If we move to x equals 5, this one's really straightforward. At x equals 5, this is a continuous function. You've probably talked about continuity from an informal perspective. Basically, can you draw the function without lifting your pencil? In this case, yes. So as we approach 5 from the left and as we approach 5 from the right, the function is approaching 1 from both sides. So the value of that limit is 1. 7's kind of a tricky one. So as we approach 7 from the left, notice we have this vertical asymptote here. The function is actually approaching infinity on the left side. On the right side, on the other hand, the value of the function is approaching 0. And so we're going to say this limit does not exist, and we'll use dne to approximate that. And I'm going to talk about that one in a little bit more detail and talk about a little bit more notation that we're going to use with problems like that. Last one here, as x approaches 9, what's happening with f of x? So 9 on the x-axis here, as the function approaches 9 on both sides, the function's getting closer and closer to 1, so the limit is 1. All right, so let's go back to that limit at x equals 7, and I said that limit does not exist, but what we're going to look at with a lot of these is what's happening on each side. And I've kind of referred to that for each of the limits we talked about so far. So this notation right here, it's like an exponent, but it's a minus sign in the exponent, is basically saying what's happened as we approach 7 from the left. Okay, so that negative means values of 7 that are just a little bit smaller than 7. And then the plus is probably what you would guess from the right. So these are called one-sided limits. And in some problems, the one-sided limit is going to be more relevant than what's called a two-sided limit. So if there is no from the right or from the left notation here, then this is what's called a two-sided limit. So those are the ones that we are doing first. So if we just want to know what's happening to f of x as we approach 7 from the left, that value is getting bigger and bigger and bigger, and it's unbounded. So as we get closer to that asymptote, the value is getting bigger and bigger and bigger. So we can say that limit does not exist, but it's a little bit more accurate to say that that limit is infinite. So we're going to say that that's infinite. It would not be wrong to say that limit does not exist. And we'll talk about some nuance there with infinity and does not exist. We'll get into that later in the course. From the right side, as x is approaching 7 from the right side, the value of the function itself is getting closer and closer and closer to 0, so that limit is going to equal 0. Now, with one-sided limits, all we care about is what's happening on one side or the other. Okay, the opposite side doesn't matter. With a two-sided limit, both of these have to match up. If both of the one-sided limits do not match up, that's when we're going to say the limit does not exist. Or at least that's one case that we're going to say it does not exist. There's other things that could make a limit not exist, but this is going to be one of the big ones.